Hi, so in today's video, we're going to look at what the domain and the range of a function are. So we've already talked about the domain in actually previous videos, but we're going to introduce this word range as well today. So we're going to talk about what a domain and what a range of a function are. So I've just put an example down here. So let f be a function that takes a real number to a real number. So I may not have actually mentioned this notation before. So this just means that f is a function. F is a function that takes a real number and as an input, so this is your input. So you're inputting a real number into your function, and you get an output, which is also a real number. So it's just notation. You probably won't see this in your A-level maths exams, but it's just notation that I use. So let this be a function such that f of x equals x cubed plus 1, where x is bigger than 0. So the key thing with this, which we talked about before, is that this here is your domain. So we have to. So in order for a function to be well defined, in order for us to define a function, we need to specify where the x values are. So we need to specify what inputs make this function exist. What inputs are we going to choose to allow this function to work? So we choose this again. This is arbitrary. Let's make a note of this again. So yeah, so we've got the function f of x equals x cubed plus 1. X is bigger than 1 is what we're going to specify, and this is called our domain. So it's our set of inputs or our set of x values in which we specify our function to exist for. So we're specifying that in order for this function we've created to exist, we're going to specify x is greater than 0. Now, let's think about what a sketch of this graph looks like. So let's say we tried to sketch y equals x cubed plus 1. So it's a cubic graph. We know it's a cubic, and it's shifted up by 1 by a vector of basically 0, 1. So we've shifted the graph up by 1. It's our standard cubic, just shifted up by 1 like this. So something like that roughly, or maybe something more like, let me try and show it again, something like this. Yeah, so something like that roughly. So we got our cubic graph here. Now, what is the range of the function? So how do we define the range? Well, it's probably what you think it would be. I mean, let me just make a note here that this is y equals the function f of x. So what is the range of f of x? Well, range is literally the range of f of x. It's literally the range of y coordinates that f of x can take. So this is obviously our y-axis. This is our x-axis. So the range, this continuous range of x values, sorry, y values, so the range of our function, the range of our y values that our function can take, this is our range. So the set of again, the set of y values, this is our range. So I'll just write this here that this is the range of our function. Now with this cubic graph, now we specified a domain x is bigger than 0. Now x is bigger than 0 here, isn't it? So that's where x is bigger than 0 because, well, that's the 0 point for x there. So essentially, we can't consider any x values less than 0. So we actually need to ignore everything here. Let's just ignore everything there because we don't need that. We're only interested in this part of the graph, this positive part of the graph, where x is bigger than 0, because we specify this in the domain. So x is bigger than 0, and this is our function here. So actually, let me just rub this out here, because really I should be writing it up here instead. So this is our function up here, y equals f of x, in the positive half. So what is the range of this function? So the range of this function in this case is actually going to be this instead. So it's going to be from 1 all the way up to infinity, and so on. So this is our range given this domain here. So if the domain is x is bigger than 0, our range goes from 1 up to infinity. So our range of values, so our range, if we were to write this in notation, so our range is the set, so curly brackets, the set of y values such that y is between 1, so it could be so it can't be equal to 1 because actually when x is 0 you get 1 there, so it can't be equal to, but it can be bigger than 1, and yeah, between 1 and infinity. I mean, infinity is not a number, so you can never actually technically equal infinity, but yes, y is between 1 and infinity, and we can see that because that is the range of our function. So when x is bigger than 0, when that's our domain, so in this domain of definition over here on the positive x-axis, we get a range between 1 all the way up to infinity. So that's an example of what a range is. So yeah, I've kind of tried to formally write what we mean by a range and domain here. So again, a domain, if you have a function f which takes x to f of x, so again, it's just using the notation we've seen before. And if we have a domain X in a set A, so A is just a set, it could be the real numbers, it could be the integers Z, so like that Z notation, it could be Q, which is the rational numbers. So as long as A is a set, or it could be just the set 0 to 1 or 0 to 10, whatever that set may be. So if X is in a set A, so X is in a domain, then the domain is X in A. Yeah, so the domain is what we specify. So if we specify that X must be in this set, then our domain is X in the set A. That's what a domain is. And then formally, what is a range? So a range for a function f going from x to f of x, where we have a domain x in the set A, then the range is the set of x values for which for which x belongs to A. So it's a set of y values, a set of f of x values, which can be obtained from our x values in our domain. So from our set of inputs, what set of outputs do we get? So basically it's our set of outputs. So it's the set of possible outputs. So set of possible outputs. So you can think of our domain as our set of inputs. So this is the set of inputs that we're allowed to input into our function. Set of inputs. Sorry, let me write that again. Set of inputs. But our range is our set of possible outputs. Let me just write this again here. So set of possible outputs, but this is our set of possible inputs. So the domain is our inputs, the range is our outputs. So what we can, so domain, what we put in, range is what we get out of our function. So our set of f of x values. So again, if this is what we're allowed to put into our function, if this is our input, then our output will be anything between 1 and infinity. So anything from 1 all the way up to infinity. And again, I'm just going to rub out these blue lines here just to make it look a bit neater. But yeah, we don't need to worry about anything on this end because our domain is telling us that x must be bigger than 0. So our range is 1 up to infinity. Okay, right, so that's domain and range. Let's look at some more examples. So let's say we've got a graph here, example number 1, and it's this graph here bounded between -1 and 1. So it's a function again. I'll just call this, let's just call this y equals f of x. So it's a function bounded between -1 and 1. I'm just going to say that that's the case. Let's just assume that's the case. And I specified a domain. So the domain is that x is in the real numbers. So what is the range of this function? Well, we can see that it doesn't go below -1. It doesn't go above 1. So our range, our set of outputs, what are the set of outputs for these set of inputs? Well, in this case, our range, I'll write it in red. So our range is going to be the set of y values such that y is between -1 and 1. Because as we can see here, the range goes from -1 up to 1. That's the range of our function for this domain. Now, again, if the domain was x is bigger than 0, so let's say it was x bigger than 0, then actually we ignore everything on this end here, and we just focus on our positive end. So our range would be between 0 and 1 instead, but because the range is every real number on our real axis, on our x-axis, it's between -1 and 1, our range there. Okay, great. Now let's look at our second example. So now our domain, we've specified a domain x is bigger than 1. So now what that means for this graph is that we actually ignore everything to the left of 1. So we ignore all of this down here, and we just focus on our graph or our function when it's greater than 1. I'll call this y equals g of x. So y equals g of x here. So this graph is I mean, it's supposed to be going up to infinity. Basically, that's why I've designed this graph. So it could be a logarithm graph, for example. I mean, we'll come on to logarithms in future videos because we've not really looked at that in this A-level math series. But yeah, it could be a logarithmic graph which goes up to infinity. So our range here is going to be, so range will be the set of y values. Sorry, just write this again, just make it a little neater. Range. So that's going to be the set of y values, so the set of y coordinates such that y is between, so 0, because so when x is equal to 0, that's our value there. So 0 up to infinity. So that's our range going all the way up to infinity there. That's our range of values because we can see that from the graph. This is just going up and up and up. So it's a set of y values such that y is between 0 and infinity, because it's going up to infinity. Now, if this was there was like an equal sign there, you would include the equal sign there, because we can see that when x is 1, y equals 0 from this function here, or the function equals 0. Yeah, that's just something to note in case you get something like that. Now, how about this one here? So we've got a function here defined for a domain when x is a real number. So for every real number on the x-axis. So it kind of, well, I mean, I've designed it such that it's supposed to be a sine graph. So let's just call this, let's just actually say straight away that this is y equals sine x. Let's just write this in here. So y equals sine x. So sine is obviously a function again, because it's a many to one mapping. So yeah, what is the range for a sine graph for this domain when x is every real number? Well, as you probably know, the maximum value of sine is 1, and the minimum value of sine is -1. So sine is bounded, this sine function is always bounded between -1 and 1. So our range for this is going to be this range here. That's our range. So our range is the set of y values such that y is between -1 and 1, and it can be equal to -1 and 1, because we know that when, for example, when sine is 90 degrees, it's 1, sine is 1, and when sine is, for example, -90 degrees, it is -1. So we can include the equals signs, the equal stipulation there. So that would be our range for this function. Again, we can see that by the sketch. The range of how high that graph goes is between -1 and 1. Now, how about this one here? So this is kind of, I guess, like a negative exponential kind of graph. So an exponential graph obviously would go upwards like this. This is like a negative reversed exponential with maybe a minus sign in front of the exponential. So how about this here? So we've got kind of like an asymptote here at +2. So it never touches +2 on this negative side of the axis there, but it's going down and down and down to -infinity. Again, our domain here is x in the real numbers. We specified this domain. So if we specify this domain, what's our range going to be? So our range, if we just look at the graph, I mean, it's going from 2 down to infinity. So this would be, again, our range. So range. So the range would be the set of y values. So set of y values such that y is between, well, the lowest number it's going to get to is -infinity, isn't it? So -infinity, sorry, let me actually write this again, just get more space. -infinity will be less than y, which will be less than 2. So basically y is going to be between +2 and -infinity, because that's the way that this graph is going. That's the range of this function here. And I'll call this function, sorry, let me just call this function y equals h of x. Just to distinguish it from the others. Okay, so that's just some graphical examples of how we can obtain a range from a graph. And it's always a good idea with these questions, when you want to determine a range, just to sketch a graph so you can actually see physically how high does your graph go. So what is the height, the basically the width of your height of your graph? What is the range? Literally, what is the range of your graph? So yeah, just a point I want to make here. It's quite obvious that the range of the function of a function depends on its domain. It's quite obvious that, I mean, if you choose a different domain, if you're given a different domain in your question, it will affect the range. So the range depends directly on what domain you specify for your function. So that's a key point. Now let's look at this example here. So let's have a function f of x equals 4 minus e to the negative x. Now, we've not really talked about these e's, this number e in this these videos on A-level maths series, but we will in future videos. So e is about 2.7. That's all you need to know for now. We'll come on to e's in more details soon. So find the range of this function for when x is a real number, so when that's our domain, so the set of real numbers, and find the range when the domain is x is greater than 0. So we've got two questions here. What is the range if x was to be every real number, and what is the range for when x is greater than 0? So again, as I kind of alluded to back here, finding a range is always a good idea to sketch a graph, because that can help you find out what your range is going to be. So it's always a good idea to have a rough sketch of what your graph would look like to determine your range. Okay, so yeah, let's sketch this graph y equals 4 minus e to the minus x. So y equals e to the x is just an exponential graph like this. So remember, e is about, let's just pretend it's about 2.7. So you've got y equals 2.7 to the power of x. We would have seen these in school maths, in GCSE maths, whatever you took. A number bigger than 1 to the power of x, you're going to get this kind of positive exponential shape because you're just continuously multiplying the number by itself, so you're exponentially growing. Now, what happens if you put the minus sign in front of the x? Again, we'll come on to this in more detail when we do with when we're going to deal with function transformations. But when you put the minus sign there, you're reversing the x-axis, you're reversing the x-coordinates. So you're actually flipping it. You're flipping these x-coordinates over to these x-coordinates there. So you're doing like a transformation. So you're basically reflecting the graph in the line y equals x. This is the y-axis, and this should be the x-axis there. So you reflect, sorry, not the line y equals x. Sorry, you're reflecting it in the y-axis. Sorry, I should say. You're reflecting it over this vertical y-axis to get a reflection, and you get this reflection here. So now this is a decreasing, like an exponential decay, basically. So this could be an exponential decay graph. So now it's decaying down like that. And remember, it goes through 1 because when you substitute x equals 0 into this and also into this as well, anything to the power of 0 is 1. So that's why we get the 1 there. Now, if we put a minus sign in front of this one, what happens? Well, when you put a minus sign in front of a function, you flip it upside down. You flip it over the x-axis, so you flip it upside down. So now the graph is going to look something like, sorry, this is an error here. I've made a mistake here. I don't know why I've done this. This is a total error. You want to flip it upside down over your x-axis. Sorry, let me redraw this. So you've got your x-axis, so you're going to flip it upside down. So what you're going to get is 1 there, and you're going to get something like this. You're flipping it upside down over your x-axis, and again, it's going to level off and never quite touch 0, but it's going to look like that. Yeah, so apologies for that. It should look like that instead. And then, okay, so y equals 4, so plus 4 minus e to the minus x is a graph translated upwards by a vector of 0, 4. So it's just going upwards by 4 units. So we're just shifting this one up by 4 units. So now what is that? What is that graph going to look like? Sorry, this should be a 4 there again. This is a mistake. It should be a 4. So we've got this graph here with 0. We've got like an asymptote at 0 because, again, when you substitute in massive numbers into this thing here, so massive x values in your power, so minus 2.7 to the power of minus basically infinity, you'll never quite get to 0, but you'll eventually kind of asymptotically approach it, but never quite touch it. So yeah, we're going to have this asymptote of 4 because remember, we're shifting this graph up 4 units, and so our graph is going to look something like something perhaps like this. You're going to have your point of intersection there at 3, and this is going to be our graph y equals f of x, where f of x is this 4 minus e to the minus x function here. Now, what is our range if x is a real number? So if x is every real number on the real number line, if we can have any input we like on this x-axis, if we're allowed any input in our domain, if this is our domain, what y values do we get? What is our range? What is our set of outputs? Well, if x can be any value on the real number line, well, it means that we can have any range here. So the range is going to be anything from positive 4 down to basically minus infinity. So our range here would be the set. So the range is the set. Let me just make a note of this. The range, let me write that again. So range is equal to, or is the set of y values such that y is between minus infinity, and I'll write that again here, minus infinity, and positive 4. You can also write it like this. You can also say that f of x is between minus infinity and minus 4. That's also fine as well for your range. If the question says write your answer in set notation, just make sure that you do write the curly brackets with this set notation instead, because this is set notation here with the curly brackets. So that's our range for this one. Now, how about the range for question number 2? So the range when x is bigger than 0. Now, in this case, the domain has changed. This is 0 on the x-axis here. So we're only interested, I'll do this in green now, green. So we're only interested in these set of x values here. We're not worried about any of these here. So we're only focusing on this positive part of the graph here. So what is our range? Well, in this case, our range is between 3 and 4 because it goes between 3, because the function goes between 3 and 4. As we can see, the height difference is 3 up to 4. So our new range with this domain is going to be the set of y values such that y is trapped between 3 and 4. So in other words, f of x is between 4 and 3. So that's another way you could write it as well. So yeah, this is just a case of analyzing the ranges and analyzing what ranges we would get for different domains. So yeah, the key point is that the range is your set of outputs and the domain is your set of inputs which you specify. And depending on which domain you have for a function, which set of inputs you specify, you will get a domain which a range which is correlated to that, which depends on that domain. So your range again is your set of outputs. So basically the range in which your graph is going on your y-axis, the range of y values, and your domain is the set of x values, your set of inputs into your function that you specify, or what the question in the exam will specify.